got the backpack.
All right, so let's take a look at what it was we were talking about last time with the relationships with these triangles. So the whole story last time was about when an altitude is drawn to the hypotenuse of a right triangle, you get three similar triangles. So let's just talk about some of those conversations right now. Our altitude is going to be this side here. This is the altitude that's drawn from the right angle to the hypotenuse of a right triangle. So it's important to understand these vocabulary words as I'm talking about them. And we want to talk about what ends up happening when I draw this altitude from the right angle to the hypotenuse of a right triangle. I end up with three triangles. I have a large triangle, a medium triangle, and a small triangle. And my large triangle is my original big guy. Here's my medium and here's my small. When I talk about that altitude to the hypotenuse, that altitude serves double duty. He is the long leg of my small triangle, and he is the short leg of my medium triangle. So our first conversations were all about that side length there. That altitude is going to divide that hypotenuse into two different sections. This one section is the short leg of my small triangle. That is this guy here, T. The second section is going to be this long leg of my medium triangle, and that guy there is S. When we start matching up some other legs, oh, by the way, this long, my original hypotenuse, we'll call that X. So now what I need to find left is my hypotenuse of my small triangle, which also happens to be the short leg of my medium triangle or of my large triangle. That's Q. And then my only one left is going to be R. R happens to be the long leg of my big triangle and the hypotenuse of my medium triangle. So the theorem we talked about yesterday, the first one was when the altitude is drawn from the right angle to the hypotenuse of any right triangle, it creates 1, 2, 3 similar right triangles. And then we start talking about some cool relationships that exist between them. So when you use the following terms to fill in the blanks, I want you to go ahead and work with the vocabulary of short leg, long leg, hypotenuse, small, medium, and large. So what does X represent in our big triangle? Thank you. The hypotenuse of what? Our large triangle. What does S represent? That is my long leg of what? Of my medium triangle. And what is T? Is my short leg of which one? My small triangle. 3 of those variables do double duty. 3 of those variables represent 2 sides of the triangles. What are the variables? Y is one of them. Q is another. And the third one? Yeah, R. And those ones are going to be our geometric means, and we can fill in those relationships. By them being a geometric mean, this is what we're talking about. That geometric means that it fits in the template where it is in the denominator of one fraction and the numerator of the other fraction. And geometrically, when we solve for it, this value squared is going to be equal to the square root of the product of these two. So we can fill in those values. This is the one that we liked to talk about being our loop-the-loop. We said that y was the loop-the-loop, which means that this altitude y is going to be the geometric mean between s and t. And we can see that this whole proportion is about long leg to short leg, long leg to short leg. So we can fill in s and we can fill in t to complete that proportion. When we start looking at r and q are my long leg, short leg of my big triangle, but notice they are the hypotenuse of my medium, hypotenuse of my small triangle. That's why they're going to be compared to x. So it's long leg to hypotenuse, and then long leg to hypotenuse. So when we fill in r, sometimes we like to talk about a shortcut. We say r is the geometric mean, and listen to the verbiage because maybe that'll help you. R is the geometric mean here between the piece that it's touching. See how r and s are touching? R is the geometric mean between the piece that is touching and this whole length. R is the geometric mean between the piece that it's touching and the whole length. Same goes for Q. Q is the geometric mean, come back up here, between the piece that it's touching and this whole length here, X. So the hard part about this is setting up the proportions. Solving the proportions is not a big deal. So here's our Unit 6 poster. Whenever we solve proportions, you know we do cross products. And each of those proportions can be expressed in a bunch of different ways. Whether we exchange our means, whether we exchange our extremes, or whether we do the reciprocal property, and each one of these has another one that it could represent. Think about the difference between a ratio and a proportion. Your ratio is a comparison of two values using division. Your proportion is when you set those two ratios equal to each other to solve. So if theoretically, if you can write the proportion, then you can solve for those values by doing cross products. All right, so we're going to take a look at this. It's similar to a problem that was on the notes yesterday, but it's a little bit different. Let's talk about writing these proportions. If I want to find this height of the ramp, I know that that is going to be the geometric mean. We can call this x and this y. We don't have either of those values, so we can't do it. So until I get x and y, I know that they have a sum of 13, but without knowing specifically what x and y are, I can't solve it. I don't have this leg, so I'm not going to be able to get x, which means my only choice is to start with 11. So I know that 11 has to be the geometric mean between what two sides, what two values. With your group mates, tell each other what goes in the other part of that proportion on your mark it, set, go. 11 is the geometric mean between the piece that it's touching and the whole. 11 times 11 is equal to 13 times y. Divide each side by 13. 121 divided by 13, 9.31. It's going to be equal to our y value. Once I have 9.31, all I need to do is subtract that from 13. And I get my x value of 3.69. Now I'm prepared to solve for h. So there's my template for my proportion. Talk to your group mates. How am I going to solve for h? And use the loop if that helps you remember. Go ahead, talk to your group mates. All right. So we can apply these proportions and use them when it comes to solving for our different lengths. If I'm looking for my height, I can use the two pieces of the hypotenuse to set up this proportion to solve for that. If I don't have either of those pieces, I can get the piece by using the other geometric mean. Yesterday's lesson was about just these two ideas. They're tricky and they're complicated, and you can get better at them by doing your homework. God bless you. Which leads us to side 2, which is a key to your homework. So go ahead and take out your homework, and I'm going to come around and check in with everybody, and you can check for your answers on your mark, set, go. First thing that we needed for number 1 is for you to write a similarity statement for the 3 triangles. And this kind of a triangle is a hard one to see because it's hard to tell short leg, long leg, small, medium triangle. The large triangle is obvious and the hypotenuse is obvious. It's opposite the right angle. But it's hard to go short leg, long leg. So just like I suggested when we did the notes, draw a more exaggerated version of the triangle. And it'll help you to see where your short legs are. BC and DB and DC. Those are short legs. It'll help you to see where your long legs and where your hypotenuse is. That way when you complete these proportions, that should be easier. Thumbs up if that makes sense to you. Okay. That should have been a strategy that you knew how to do because that's just similar triangles from last unit. All right, when we look at A and B, A was a loop-to-loop. Here's my altitude to the hypotenuse. My x is going to be the geometric mean of the 2 pieces. So x is the geometric mean, those are the 2 pieces. Hey, take a minute and look at B. It's wrong on your key. Because this x is going to be the geometric mean between the piece that it's touching and this hole. So on the key I did 30, but it needs to be 42. That's a most missed error. If you're going too fast, you'll make that mistake too. That radical is also not simplified properly on your key, so I want to make sure that you can get that straight. That x is the geometric mean between the piece that it's touching, that's the 12. And that makes sense because it's short leg, hypotenuse, hypotenuse. Short leg, hypotenuse, hypotenuse. Okay, so this next problem was our lazy man's way of trying to get a couple problems out of one diagram. So not this. But what ends up happening is we gave you a combination, and it's crazy, with just two values of the hypotenuse piece 1 or 2, or my first or second leg, or my altitude. That's where that H and A come from. We can give you very, 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 very limited information, and you can go ahead and figure out what everything is. So for our first triangle, I know that my hypotenuse is 12. The first piece is 4. I can figure out the second piece is 8 super fast. So this first leg is the geometric mean between the piece that is touching and the hole. This second leg is the geometric mean between the piece that is touching and the hole. That's where my 12 and 8 come from. And then this altitude A is going to be the geometric mean between those two pieces of the hypotenuse, H1 and H2, 4 and 8. So hopefully with those proportions, you can go back and solve to find those answers. Let's talk about B. In this version of the triangle, we gave you H2 was 3. We gave you L1 was 6 roots of 3. So the first thing I'm going to solve for is H1. So I know that 6 roots of 3 is the geometric mean between the piece that it's touching, that's this, and the hole, which is going to be H1 plus 3. Once I solve for H1 here, I'm going to use that value to solve for my altitude. Once I solve for H1 here, I'm going to use that value to solve for L2. The application of this properties. Definitely fairly tricky. So this proving is an interesting conversation, and it might do you better to, instead of using these values, it might do you better to use the values that were on your warm up yesterday and your triangles. You have a Y here, an S, a T, and an X. And I believe, is this one R and this one's Q, or did I get it mixed up? So I'm going to encourage you to think about this one, study the notes I put on the key, and we'll come back and talk about it later. But this is definitely a challenge problem. Sometimes we like to put the challenge ones in the middle of the homework because if they're at the end, people just skip it and don't get to it. But we'll come back and talk about that again. First, we'll scoot through these ones. This homework was a little bit upside down. The end of it was easier. So if you made it this far, it was downhill from here. Hey, this picture here is how you can measure the height of something. If you stand at any distance from something and you measure at a right angle, if you know how far you are from something and your height at which you're holding it, you can use your loop-to-loop theorem to figure out what this second piece of the hypotenuse is, and then your total height is those two added together. It's kind of cool. All right, take a minute and look at 6 and 7, A, B, and C. See if you can understand where those proportions come from. 4 is the geometric mean between the two pieces of the hypotenuse. X is the geometric mean between the two pieces of the hypotenuse. Skip down to 7C. 8 is the geometric mean between the two pieces of the hypotenuse. Those loop-the-loops help you remember what goes where. 6C, 7A and B. use our theorem that talks about the ratio between the hypotenuse and long leg of the big triangle to each of the small and medium triangles. X is the geometric mean between the piece that is touching and the hole. X is the geometric mean between the piece that it's touching and the hole. X is the geometric mean between the piece that it's touching and the hole. So you have a quiz on this next class. So I would encourage you to make sure you understand how to do this. Maybe open up a blank copy of the homework, practice, and go back and check the key. Let's check out this word problem at the bottom. The altitude and hypotenuse of a right triangle is 6 feet. So let's go ahead and draw, and I'm going to draw our picture in a more exaggerated, so it's easy for me to tell the difference between what is my right leg or short leg and long leg. The altitude to the hypotenuse of a right triangle is 6 feet. The short leg of the smallest similar triangle is also 6 feet. Sketch the triangle and find the measure of the hypotenuse of the large triangle. So I'm looking for this. So we'll go ahead and first solve for that. So 6 is going to be the geometric mean. Between the two pieces of the hypotenuse. Here's our loop-the-loop. Huh. Pretty interesting, huh? So even though my picture was exaggerated, it turns out that each of these triangles are going to be congruent, because A is equal to 6. Therefore, what's X equal to? Sound okay? Question, go ahead.
Just kind of on topic, but also kind of off topic. How would you classify two legs differently if they were both equal? Because they don't have a short or a big. You have two.
Right. So if you have a triangle like this, like let's sketch what this one really is, right? So this one really is a right triangle where this altitude to the hypotenuse divides these two legs evenly. So you're not really going to have, it's super hard to tell the difference between your similar sides and your corresponding sides. But if I know that this is 6 and this is 6, interestingly enough, so was this. Do you see how I have two isosceles right triangles?
Yeah.
So each of these triangles, these two ones are actually going to be congruent. So if you want to call this A, you can call this A too. So you don't need to differentiate between all the different sizes. And the rules are still going to apply. This is going to be the geometric mean between these two. This is going to be the geometric mean between the piece and the hole. So your hypotenuse lengths are going to be larger. And we're going to talk about that today. You're going to learn today that these lengths are 6 times the square root of 2. We have a shortcut that tells us that. And that's our lesson today. Okay? Any other questions on the homework? Does it seem better now that we've talked about it? Okay. I encourage you, if you did not give it your full best effort, your biggest brain, I would go back and find some time to put some more effort into doing it. It's not difficult once you get that concept, but if you haven't given it your full brain, you owe yourself that. Yeah.
I know you mentioned this, but can you please explain when you're allowed to do the loop trick?
Both of them are loop tricks. This loop-to-loop is the altitude from the right angle to the hypotenuse. That's going to be the geometric mean between these two pieces. So that's what you see here in C and B and A. So anytime I'm talking about the altitude that goes to the hypotenuse, that segment that I drew, that's going to be that geometric mean between the two pieces of the hypotenuse. The pink ones here are this leg of my biggest triangle is going to be the geometric mean between this piece that is touching and the hole. So this is like a leg hypotenuse. The other one is an altitude conversation. So if you understand the similarities between A and B in 6 and C in 7, and A and B in 7 and C in 6, if you can see the difference between each of those proportions, then that'll answer your question. Sure. All right, so here come today's notes. All right, so do you remember a couple of lessons ago, we talked about the idea of, are all isosceles triangles similar? The answer was no, because those angles could be different. And then I said to you, okay, how about all isosceles right triangles? Are all isosceles right triangles similar?
Yes.
And you said yes, because why? Side angle side similarity. Angle angle similarity, right? Because we can talk about them fitting. So we're going to combine that idea and put some Pythagoras in it, because remember our goal is I want to know lengths of sides of triangles. That's what it comes down to. I want to be able to figure out lengths of sides of triangles. So we have some Pythagorean connections. These are some connections that you've already seen. Would you all do me a favor, please, and add some sweet little 2's on here? Somehow my squares got left off. Would you please, with your group mates, talk about each of these different iterations of Pythagoras and when and how they are used? On your market set, talk. All right, so talk to me about this guy. When did we use him? To solve for sides of triangles, true? All right, talk to me about this guy. When did we use him? That's distance. How about this guy? If C is smaller, what is it? How about this guy? If C is bigger, he's going to be. Okay, so here we go. We're going to start talking about two specific kinds, two special kinds of right triangles. And I would like you to do right now is with your group mates, come up with at least 4 different truths or facts about this triangle. On your market set, go.
It has 2 45-degree angles, opposite the right angle, and oh yeah, we did truth. These are each 45.
So I was eavesdropping, and I heard a lot of people say it's isosceles. So right away you know that these 2 legs mean that they are isosceles. What do you get from that fact? 2 base angles are going to be congruent. And then tell me about their measure. Yeah, I know that both of those angles are going to be 45 degrees. Talk to me about A and B. Yeah, they're going to have the same length. So the A's value and B's value are going to be the same. Okay, it's an isosceles right triangle. I know that the 2 congruent angle measures are 45 degrees, and I know that A is equal to B. I like all that information. Okay, our next conversation says, go ahead and let x equal the length of the legs of the triangle. So because A is equal to B, and they're the same value, I can go ahead and say, let's call both of these angles, or both of those side lengths x. Are you okay with that?
Yeah.
So my next instruction is to solve for the length, there's only one of it, solve for the length of side C in terms of x. So what that means is I'm not going to be able to come up with an answer, I'm just going to call it in terms of x. So if I know that c squared is equal to a squared plus b squared, so says Pythagoras, then I know c squared is equal to, if I can put x in for those side lengths, are you okay with me substituting that?
Yeah.
Okay. If Donovan has 1x squared and I have 1x squared, how many total do we all have together? Yeah, together we have 2x squares. Remember we talked about you can solve using a property of equality that allows you to take the square root of each side. So the square root of c squared is c. And then here's something tricky to understand, because underneath my radical I have a 2 and an x and an x. What can come out of that radical? Just my x. Who's left inside? My 2, because here's my double factor and 2 has no friends. Are you okay with that?
Yeah.
So that means that the side length times the square root of 2 is always going to be equal to the length of your hypotenuse. So if I only have one side of an isosceles right triangle, I can use this story to always figure out what my side lengths are, because the ratio of A to B to C, A and B are going to have the same side length, and C is that side length times the square root of 2, which means they have a 1 to 1 to root 2 simplified scale factor. This is the story that we're going to be using when we talk about this. All right, so we'll turn the paper over, and here's our first part of our story. If we have a 45, 45, 90 degree triangle, that hypotenuse is going to be root 2 times as long as each leg. So here's my 45, 45, 90 degree, and I have an x and an x and a root 2. Let's do some practice ones, and they go like this. If I have an isosceles right triangle, and I have a side length of 3, what is my other side length? What is my hypotenuse? 3 times the square root of 2. Let's try it again. If I have a 45, 45, 90 right triangle, and I have a side length that is 4 roots of 2, what is my other side length? What is my hypotenuse? What does that equal? Root 2 times root 2 is 2. 2 times 4 is 8. Let's go again. If I have an isosceles right triangle, and I have a hypotenuse that is 6 roots of 2. What are the lengths of my legs?
6 and 6.
If I have a hypotenuse value of 5 in an isosceles right triangle, how do I find x? Five is equal to square root of 2 times that x. I heard divide. So I have x is equal to 5 over the square root of 2. Am I allowed to leave a fraction looking like that? How come? What's the matter with that fraction? I can't have an irrational number in the denominator, so I'm going to do this to it. What does that give me for my x value?
How do you get square root of 2 over the square root of 2?
I made it up. I multiply this by 1. This guy needs another square root of 2 in order to get it out for the radical sign. So I'm going to give it to him. But I can't just go around multiplying things by however I want. That changes the value. So root 2 over root 2 is worth 1. When I multiply this by this, I end up multiplying it by 1, which in the end doesn't change its value. It gives me 5 square roots of 2 over 2. Do you see it now? It's the same philosophy that we use when we find a common denominator with fractions. We multiply the numerator and denominator by the same value. All right, let's scoot down.
Wait, do you actually leave it like that, or do you have to multiply both sides by 2?
So right here
Wait, never mind.
is my final answer. So let's skip down to number 1. 45, 45, 90. Isosceles right triangle. What is x equal to?
7
45, 45, 90. Isosceles right triangle with your partner. Tell me what x and y are equal to. That 10, that side length of 10 is equal to my x times the square root of 2. Knowing that relationship, I immediately get an equation that I can solve by dividing by each side by the square root of 2. When I divide 10 by the square root of 2, I can't leave that like that, because in today's world, you are not allowed to have a radical in your denominator. Maybe in your children's world it will have changed, but right now, no luck. Root 2 over root 2 is worth 1. Anything times 1 is itself, so I'm not changing the value of that number, but I am changing what's in the denominator. Root 2 times root 2 is 2. 10 roots of 2 over 2 is not simplified because 10 and 2 are friendly numbers. Once I've solved for x, true or false, I already know y. Because it's isosceles, x and y have the same value. That's our first special right triangle rule. How you doing with it? Okay? I can solve for all three sides, given only one. This is what we're doing here. I can solve for all three sides, given only one, because I have this story. It's a 1 to 1 to root 2. X to x times root 2. If you give me any one side of an isosceles right triangle, I can give you the other two. Because they are similar to every other isosceles right triangle. And I can use that pattern. Sound okay?
So for like on this sheet, you only want us to put a simplified radical if that's our final answer, whereas if we need that number to calculate other things, we just do the simplest form. Okay.
Okay? All right. Special right triangle number 2. Do you see this very light, faint outline on your notes? Do you see it on your notes? Yeah. That is the second half of this triangle. Picture it as a mirror image. Now here's a cool thing about triangles. When we name them, the vertex opposite of the side has the same letter, just capital instead of lowercase. And we're mainly talking about this 30, 60, 90 triangle today. But the relationships that we get between the sides are a part of what we already know is true when we look at it as half of an equilateral triangle. So with your group mates, go ahead and give me 4 features of this triangle and you mark it set talk.
It's right, square, A equals 30, C equals... Oh, it's right, it's... This is what I get.
Well, we can't just say measure of angle A is 30, because there's 3 angle A's. So it's
Oh.
angle
BC.
CAC and angle, just find another look at that one. Those ones are 30, but then there's also a measure of angle
Just
A
talk
that's
about
60.
one triangle. So just talk about my main triangle that you have on your notes.
Okay. That goes on your right special. So yes.
So interesting conversation here. When we're talking about this triangle, I just want you to talk about what's in your notes in black, but understanding how it's half of this equilateral triangle helps us understand one of the pretty cool relationships that we're about to understand. So I want you to know that that triangle is a right triangle. And over here we were talking about whether or not we could call it angle A. We're going to say yes we can just because we're talking about that one triangle, but Nora's right. There are 3 angle A's pictured in that. So if you want to make sure that we call it BAC, you can do that. It's scalene. Doesn't have the same angle measurements. But once we know it's half of the equilateral, that gives me a conversation about side length. Because, follow me here, it says let x equal the length of the short leg of the right triangle. So we're going to call this x. If this is x, then what would this value be? Yeah, that would also be x. So then what would the length of the equilateral triangle be? X plus x, or, so that's going to be what this guy's value is. Think about for a minute how I got that. If we call this x and this x, then this whole length is 2x, and because it's an equilateral triangle, I need to pretend I can see this pink triangle in order to see that that relationship of C is double the length of A. So now it's telling me to solve for the length of sides C and B in terms of x. I got C, no problem. So I'm going to go back to my Pythagorean theorem. C squared is equal to A squared plus B squared. I know C is 2x. I know A has a value of x. And B is the one that I don't know this time. So 2 squared times, or 2x times 2x is equal to 4x squared. How do I get B by itself? Subtract x squared from both sides. If I have 4x squareds and I subtract 1 away, what am I left with? 3x squareds. 3x squareds are going to be equal to b squared. I'm going to jump back and use that property of equality that says if you're solving for a variable and that variable squared, you're allowed to take the square root of each side.
How did you get the 4x?
2x times 2x is equal to 4x squared. So the square root of anything squared is equal to that thing, so I end up with b. And just like up on my top one, if I have a 2 and an x and x, what can come out of the radical sign here? And what's stuck inside? So if this has a relationship of x, this has a relationship of 2 times that x value, and b is going to be that short leg times root 3. When I talk about the scale factor between the legs, A to B to C, if A is x, C is double whatever x was, and B is x times the square root of 3. If I want to know a simplified scale factor, 1 to root 3 to 2. Now here's the deal. Everything on this side of the page is just telling you how we got the shortcuts. So most of you are one of two kinds of learners. You want to know, I don't need to know how you get it, just tell it to me and I'll memorize it. Or I can't memorize it unless I understand why it's there. Are you a detail person or are you a whole concept person? Because if you're a whole concept person, this is why it works. If you're a detail person, this is what you need to know. Theorem 7.3 says in a 30, 60, 90 triangle, the hypotenuse is double the length of the shorter leg and the longer leg is root 3 times the shorter leg. So if you are a detail person, you just tell me what the relationship is, there it is. Let's do a few. If I had a 30, 60, 90 triangle and my short leg was worth 5, what is my hypotenuse? What is my long leg?
Five times the square root of 3.
5 times the square root of 3. If I have a 30, 60, 90 triangle, and my hypotenuse is worth 16, what is the length of my short leg? What is the length of my long leg?
80 times the square root of 3.
If I have a 30, 60, 90 triangle, and my long leg is worth 12 roots of 3, what is my short leg worth?
12,
What is my hypotenuse?
24.
Mason's got it. Come on down to C. I have a 30, 60, 90 right triangle. And 9 is my long leg. So let's talk about what we know. My short leg is x, my hypotenuse is 2x, and my long leg is equal to x times the square root of 3. There's your equation built into it right there. So if 9 is equal to x times the square root of 3, how do I solve for x? Divide each side by the square root of 3. So x is equal to 9 times the square root of 3. Everybody okay with that answer? Math gods? What do they need us to do? Yeah, we need to rationalize that denominator, so we're going to go ahead and multiply it by root 3 over root 3, which is going to give us 9 times the square root of 3 over 3. Everybody okay with this answer? What is x equal to? 3 times the square root of 3. So if x is equal to 3 times the square root of 3, how do I double that? How do I double that? If you have 3 roots of 3 and I have 3 roots of 3, what do we have together?
6 roots of 3.
6 roots of 3. It's going to be equal to RT. Yeah.
Why did you equal x to the square root of x to the square root of 3 to 9?
Because, why did I equal what?
9 equals.
Because the long leg is equal to my short leg times the square root of 3. That's the formula that we have up in our theorem that we proved on the other side. All right, if my long leg is equal to 10 times the square root of 3, that's going to be equal to my short leg times the square root of 3. If I go to divide by the square root of 3, what do I get for my short leg? What's x going to be?
20.
Double that. 20. All right, let's talk about this last problem. If the window shown is a square, find the area of the window. So let's talk about if it's a square, this side and this side and this side and this side are all congruent. This side and this angle and this angle and this angle are all right. So this looks like it's the hypotenuse of 2 isosceles right triangles put together. And that hypotenuse's length is 36 root 2. What is the side length of my window?
45.
It's a 45, 45, 90. Keep going. So if this is 3 roots of 2, what's my side length? Or 36 roots of 2, what's my side length? So my area of my window is going to be 36 squared. Inches squared.